Hello guys and welcome to my YouTube channel. So today I have a very interesting video for you. Cambridge decided to be a little bit sneaky and they had a lot of graphs in this question, right? It's question 3 of February March 2018 question paper 4.2. So they had about 3 graphs and another 4th graph where you weren't required to sketch anything but you had to analyze it. So we're gonna do it a little bit so that we can be able to understand how to solve some of these graph problems. Let's begin. Starting off with the first question, question 3a, we're given a mass that is undergoing a process known as simple harmonic motion. If you have encountered simple harmonic motion, then you'll be fine. If you haven't, you're in luck. Well, simple harmonic motion is defined as a process where you have an object that is undergoing a very simple yet harmonic motion, right? So how it works is that, for example, if you have a pendulum, right? The acceleration is supposed to be directly proportional, right, to the displacement. But guys, it's in opposite direction. So if displacement is positive, acceleration will be pointing in the opposite direction. It's going to be negative. That is what simple harmonic motion is. So we've been asked to show the variation with displacement x of the velocity v of the mass. So that mass that is undergoing simple harmonic motion, we are asked to show the variation of displacement with velocity. So if I'm looking at this graph correctly, right, I'm going to start by plotting points that I know, right? So I know that if I'm at the maximum point, the maximum displacement, on a pendulum, you have to stop, right? So that you can be able to come back. So what that tells me, if I'm at a maximum point and I'm stopping and coming back, it tells me that the velocity is 0. So x naught here represents the maximum displacement. So what it tells me is that here, the displacement is going to be 0. Okay? Then it tells me here on the other side, on the negative side as well, is going to be of 0. Right? So draw little points so that they're clearly visible. Right? And then at the equilibrium point, if you're going in this direction, right, your displacement is going to be, your velocity is going to be positive because we've defined a positive and a negative direction, right? So if you're there, your velocity is going to be positive and it's going to be the maximum at its equilibrium because it passes through the equilibrium fastest, then it decreases as it goes over there. It's decelerating because acceleration is in the opposite direction. Then on the other side, we also have something like so. And then a problem arises. How do I connect these 4 points? You could do it like that, right? Sharp points all along, which is a very good possibility. You could do it like this, curves inside. You could do a lot of things that you want. But here, we draw an ellipse. We connect them in sort of a reasonable circle or an ellipse. Why do I do this, right? I know you're going to ask why. If you've been watching my channel long enough, you know that we shouldn't just do things without understanding why. But for this one, I'm going to say it's a little bit tricky because I could go through it, right? It's a process known as finding the equation of an ellipse. The relationship between the velocity, we're asked to know that it's v is equals to omega, the square root of the displacement, the maximum displacement squared, right? With this relationship. But somehow, what I just want you to know is that this relationship is the equation of an ellipse. It can be rearranged into the form of the equation of an ellipse. We're not going to go through how we do that, but what you need to draw here is an ellipse. So for this one, I'm just going to ask you to take it with a grain of salt. But if you need to understand, put in the comment section below. I might create a video on this just for those who just want to understand it, right? But I'm just going to ask you to join it like so. So it's technically not really a circle, but the marking scheme does specify that if you draw a reasonable ellipse, they will be able to mark for you, right? So an oval shape or a reasonable circle, you will get your full mark. Okay. Moving on to part B, we're given a straight, stiff wire. Very straight and stiff, right? Let's say that's our wire. It passes through a region of uniform magnetic flux density. So I'm going to have a magnet, a bar magnet, one magnet on that side, and they're going to create a region in between of uniform magnetic flux density. We know that magnetic flux density defined by the symbol B. Okay, so the angle between the direction of current, so this wire is connected in a circuit so that current can be able to flow through. So the direction of current and the direction of the magnetic field is varied. So you're sort of turning your wire, right? Like so that you can be able to get a different angle with the magnetic field. So it's going to have an effect on the force that you're going to get. So what are some of the facts that we know? We know that if the wire is parallel to the magnetic field, no force is experienced. If the angle between the direction of the magnetic field and the wire is 0, then we won't get a force. So that's a point that I can put here. Okay? If there is no force, that means there is no angle. And the maximum force that we get, our expression to get our force, a relationship was developed which says F is equals to BI-L sine theta. Right? So we know that sine 90, the maximum value of 90 here of sine is 90. So that's where we're going to have 1. That's our maximum force. But then if sine is 0, sine theta is 0, that's how we're going to have an force of 0. Right? Sine 0 is 0. And if you ask me where does the relationship come from, it was done during experimental observation that there are 3 things that affect the force. They found that it was the magnetic field, they found that it was the current itself and the length of the wire, as well as the angle. And they found that it was a sine relationship because you had to resolve it so that it's perpendicular. Okay, so they got that relationship. So I know that at 90, I'm going to have a maximum force over here. And what I'm going to draw is a curve of decreasing gradient, right? Why decreasing gradient? Because it's a graph of sine, guys. A graph of sine goes like this. So I'm going to draw like a sinusoidal graph like this, a graph with decreasing positive gradient like so. Okay, so, and I hope it makes sense, right? We draw it because of the graph of sine theta. Move on to another graph. Oh, these guys were very cheeky. We're given a sinusoidal supply that is a frequency of 250, right? And I know the relationship between frequencies. So always ask yourself, I want to draw a graph. What are the key things that I need for these graphs for alternating varying voltage? What you're going to need is the period. Okay, and I know that F is equals to 1 over T. So my period T is actually 1 over F. So if I say 1 over 250, I'm going to get my period, right? And my period is 0.004. Okay, 1 over 250, which is 4 milliseconds, right? That's my whole period. So if I start here, my whole period is supposed to end here. So my half period is going to occur here. Right, so I'm going to have a sinusoidal graph like so, passes through there, then goes through like that. Okay, but then I'm going to ask myself, but where do I start and where do I finish? I started 0, 0, okay, which is very important, right? Where at time t is equals to 0, there is no voltage. It hasn't begun yet. And then the root mean potential difference, I'm going to create some videos around this concept as a whole so that you can be able to understand it. But for now, V RMS is equivalent to V naught over the square root of 2. That's a relationship that I ask you guys to just take it with a grain of salt. I will explain in future videos where this comes from, right? But then here we're going to get a value of V naught, which is going to be equal to root of 2 times the VRMS. So I'm going to have root 2 times 2.8 being equivalent to 3.959, so forth and so forth. So I can just round this off to 4.0. So my maximum here, my maximum V is going to be 4.0, going to occur here. My maximum V here is going to be minus 4.0. My maximum V here is going to be 4.0. So I'm going to draw my curve like so. Sinusoidal graph, right? We have a lot of key points. One of the points being here, another point being there, another key point being there, another key point being here, here, and here. Very important. So I asked myself, what is my period? I got it. What is my maximum amplitude? And I got it, and I draw a reasonable shape. Another graph question. These guys were on fire. The last one, they don't really require us to sketch, but they require us to understand the concept. Again, I'm going to make a lot of videos on these concepts, guys. But here we're focusing on a graph of binding energy. And I want you guys to understand what binding energy actually is. Imagine you have a burger, okay? You're going to eat a burger, right? A burger is made up of several ingredients, right? You've got buns, you've got tomatoes, you've got lettuce, the meat patty, all these various ingredients, right? So how much energy do you need to have a burger and separate it into its constituent ingredients, right? You want to separate all the ingredients aside. How much energy do you need to do that? We call it binding energy, the amount of energy that is required to break a nucleus into its constituent protons and neutrons, whatever a nucleus is made up of. How much energy do we need to break it apart? Okay, and I know it's kind of counterintuitive. Why would they name the energy needed to break something apart binding, right? Binding means bring something together. Physicists are crazy, but then crazy good, but then binding energy is just how much energy do you need to separate a nucleus into its constituent nucleons. And when you do separate them, they're supposed to reach infinity. So they're supposed to be separated an infinite distance away from each other. Include that, right? That's binding energy. So if you are stable, which is our goal in the world, right? All of our goal is to be stable. You're going to school so that you get money. Some of you, right? So you get money, you're stable, and everything is okay, right? We want stability as people, which is very okay. Start a family, all of that. So even atoms themselves, nucleuses, also want to be stable. It's everyone's goal, right? So the most stable atom that we have is iron, which rests over here, Fe, right? 56, right? With an a nuclear number of 56. Very stable, living a nice, comfortable life. And all of our goal is for us to reach the level of iron. So iron has the highest binding energy. It's stable because it takes a lot of energy. Binding energy per nucleon is how much energy do you need to take away one nucleon, separate it from a nucleus. How much energy do you need to do that? We call that the binding energy per nucleon, right? And you find it by dividing the total binding energy by how many nucleons you actually got. Just like if you want to find out how much energy do you need to remove a tomato from a burger, how much energy you need to remove maybe a meat patty or lettuce from a burger, that's the same as binding energy per nucleon. You want to remove one thing, how much energy do you need to do that? So if you have very, very high energy, it needs a lot of energy. If you need a lot of energy to remove a tomato, it means your burger that you formed is very, very stable, right? If you need a lot of effort to break up a family, that means that family is very stable, right? And that's the goal. If you have a very high binding energy per nucleon, you're going to need a lot of energy to be separated. So if you're not like iron, if you're not stable, you are somewhere else, okay? You're either on this side or on this side, where you have a lower binding energy per nucleon. You have a very little energy. So if we try to, separate one thing, is going to be harder, yes, but then the more it becomes, the more you have a lot of things over here, right? And you want to remove one thing so disjoint that it's easier to just do that, to just take one thing off, right? But when you have very few things over here, it becomes harder and harder until you reach iron over here. Okay, I'm going to explain this again in depth in other videos, but then heavier nucleons lie on this, starts to decrease, right? The binding energy starts to decrease after iron starts to get smaller and smaller and smaller, because it's much easier. They're very disorganized. There's a lot of stuff, very easier to just take one thing off. They're unstable, right? If there are very few of them, also unstable, but they become more and more stable, the stablest being iron. So if I've been asked to mark the position of uranium, it is a very high AR 235, so I expect to find uranium over here because it is a very high AR. So I'm going to put uranium over here, okay, 235, and been asked to label this point U, okay. The point BA is 141 BA, so I expect BA to be over here, right, guys? This is just okay. Then KR, I expect it to be over here. I don't need all of this, okay? So I have KR because KR has a lower A, so it's going to be on this side. Your graph has already been drawn for you. Uranium is the highest, so it's going to be on this side. And it sort of makes sense to me why it starts to decrease after iron, because you have a lot of things, right? It's very unstable. And when you're on this side, let's assume you have one person. If you want to take away one person, you're going to have almost zero. But if you have two people, and you want to take one person away from that, it's going to be slightly harder. If you have four people, slightly harder. If you have six, slightly harder. But the more they become 100, it's just easier to just take one person off. But there's like a balance point, which occurs at iron, where it's just enough amount of energy that you need for it to be stable. That's how you sort of think of these fission reactions and where it sort of places. Hope it makes sense. I just wanted to talk about this graph. There's many graphs. I just saw it and it was a very, very interesting question, right? 3 graphs in one go. It's a skill that you need to develop. Once you have it, trust me, no one can steal it away from you. Cambridge loves graphs, right? Even if we look down at this paper, we're going to encounter other graphs it just loves graphs, right? So it's a skill that you need to develop. If you still struggle with it, put it down in the comment section. Or what topic do you need me to address that has a lot of graphs? But until then, thank you guys for watching, and I'll see you in the next one.